Hello everyone. In this presentation, we will focus on the task 2.2 of the ATLANTIS project related to resiliency and self-healing by design. After having defined the resiliency and the correlation with the interdependency, we will present both mechanisms. Then, we will define the self-healing and present multiples technologies that allow to manage it. Resiliency and interdependency. The definitions clarify the difference to the risk concept, as well as add topics of considering emerging risks, goals optimization, adaptation, and transformation, improving anti-fragility, and introduces, actually a continuous cycle, of resiliency phases in time. The resiliency during a disaster event or crisis is usually considered through its phases. Phase 1, understand or plan risks, is applicable prior to an adverse event. Phase 2, anticipate, prepare, also applicable before the occurrence of an adverse event. Phase 3, absorb, withstand, comes into action during the initial phase of the event and shall include the vulnerability analysis and the possible cascading ripple effects. For example, how steep is the absorption curve and how deep down will it go? Phase 4, respond, recover, is related to getting the adverse event under control as soon as possible, influencing the how long will it last question. Phase 5, adapt, learn, which encompasses any improvements made on the infrastructure and its environment. CI functionality can be understood as its functionality level, being consisted of functionality elements, usually CI sector and service specific, that can be breakdown further to the specific indicators as presented on this slide. The indicators can be quantitatively evaluated, for example, following a ladder type of performance criteria, and then aggregated from bottom up to assess the overall CI's resiliency. The overall process of evaluating the CI's resilience can be described, as presented on this slide, following four main steps of the measurement process. The evaluation process can be organized, for example, in a 5x5 matrix, where 5 resilience phases are considered in relation to 5 resilience dimensions. See the list from A to E. For each cell of the matrix, specific indicators can be prepared and evaluated. Next, let's explain the basic terminology. Interdependencies mean the connections among agents in different infrastructures in a general system of systems. Being dependent means needing the support of something or someone to continue existing or operating, dependent upon something. Modeling means the activity of using mathematical models to make calculations or predict what might happen. Why modeling? Let us consider the system where the specific entities, CIs, are somehow related within a larger context. Here we have an example of 5 CIs that are somehow related, dependent on a one-to-one basis, thus an overall 7 dependencies. Arrows represent them and mean required input for the target CI to be able to perform. Dependency can be direct or indirect. For example, a C is dependent from D via A, but D is directly dependent from C, etc. Consider a situation where C fails. What does that suggest? We will explore that further. So, we need to define the system under analysis and its CIs next. To identify the specific dependencies among related CIs on a one-to-one basis and use the obtained information to anticipate the propagation of the effects of failures from the known threats. Now we consider the slide 6 and its graphics representing 5 CIs and 7 dependencies. If we transpose the list of CIs to the matrix on this slide, we can precisely document, for example, type of the dependency per each pair, if any, in respective cell. Let's list originating CIs by the columns and consider dependent CIs by the rows. Note different colors of related headings to present the convention used. The matrix must comply with the list of the dependencies. Recall the template on the previous slide. In our case, we wrote down 7 one-to-one dependencies identified according to the arrows on a slide 6. Now we can use the documented information. Documenting the CIs and their dependencies is only part of the work. Now we can consider the failure, accident, or attack on one or more CIs. In our example, we consider in that respect C. In the first scenario step, node C fails. In the second step, D and E. In the third step, D cause the failure of A, and in the fourth step, E should cause the failure of C, but already failed in the first step. The arrows present here a simple animation of the cascading failures propagation, covering 4 steps until it stops. Similar animation can be presented also, for example, over the map of the area. Let's have a look of the interdependency training video from JSI to have a dedicated training on this topic. Orchestrator and redundancy, Kubernetes. Self-healing is part of the resiliency of a system and refers to the process of automatically recovering or repairing failing parts. There are two main approaches in self-healing: reactive self-healing and proactive self-healing. On the one hand, reactive self-healing responds to failures as they appear and takes action to restore the system to its optimal state. On the other hand, proactive self-healing involves more attributes than reactive self-healing, such as monitoring the system and prediction process to prevent a failure from occurring. The goal of this approach is to anticipate potential failures and take action to prevent them from occurring. However, reactive self-healing approach only considers recovery tasks. By itself cannot address identification, protection, detection, or response problems. For that reason, it does not work on cyber attack scenarios where exploit vulnerabilities create persistent threats that imply data breaches, resource exhaustion, and unauthorized access that require comprehensive measures beyond restarting or replacing components. The need for increased scalability, flexibility, portability, consistency, operational efficiency, resource utilization, and application resiliency made containerization and orchestration a referent to deploy systems. A container orchestrator is a system or platform designed to automate the deployment of a system and different functionalities such as configuration, availability, scaling, security, resource allocation, load balancing, and health monitoring. Containers are portable and self-sufficient environments that include an application and its dependencies. Following this, container orchestration helps manage the lifecycle of these containers and their communication in a complex environment, ensuring they run efficiently and reliably. Kubernetes is an open-source container orchestration tool that allows to build application services that span multiple containers, schedule containers across a cluster, scale those containers, and manage their health over time. Now we will explain some of the main components that are relevant for our implementation. Node. A node is a physical or virtual machine in a Kubernetes cluster that runs containers and provides computing resources, CPU, memory, storage. They are managed by the control plane and are classified into master node, manages the cluster and handles scheduling. Worker node runs application workloads. Pod, the smallest deployable unit in Kubernetes, represents a single instance of a running process in a cluster. A pod can contain one or more containers that share the same network namespace, IPC namespace, and storage, and they can communicate with each other using localhost. SVC. A service in Kubernetes exposes applications, ensures continuous operation by handling pod changes, and defines a logical set of pods with access policies. Ingress controller. API object that describes the routing rules for traffic. Services helps to route traffic to the concerned pod container instance. Kubernetes use virtual IP address in the internal network. However, ingress controller helps to route external requests into the internal address. Link proxy. A layer that handles service-to-service communication, providing features like load balancing, service discovery, observability, and security. Linkerd provides deep insights into service behavior with tools for monitoring, logging, and tracing. It offers MTLS for securing communication between services, ensuring data integrity and confidentiality. Redundancy is defined as the state of exceeding what is necessary to function properly, in order to prevent the failure of an entire system due to a single component failure. In this context, network redundancy is the process where additional instances of devices or equipment are installed within the network infrastructure. The additional instances serve as a backup mechanism to swap the network's operations in the event of a network failure. The primary purpose of network redundancy is to ensure network availability and reliability by minimizing the risk of downtime or service interruption due to failures or maintenance activities. The objective of redundancy is to improve the protection of the system against vulnerabilities using redundancy deployments. Kubernetes addresses self-healing through its components. Key to this functionality are liveness and readiness probes, which continuously monitor the running status of a pod. When a pod is failing, Kubernetes replaces it using another one. However, what if it is not a stochastic failure? Replacing the pod will not solve the problem, and the pod will be continuing entering into a failure status. The Kubernetes self-healing process covers the reactive self-healing approach. However, it does not work for cyber attack scenarios where exploit vulnerabilities create persistent threats that imply data breaches, resource exhaustion, and unauthorized access that require comprehensive measures beyond restarting or replacing pods. That is why we analyzed the state-of-the-art concerning the self-healing system and proposed an approach that takes into account the MAPK loop features using the easy deployment processes of Kubernetes. When an anomaly is detected in the monitoring system, Our approach will apply automatic changes such as operating system, OS, libraries, and versions of system or system configurations in the Kubernetes environment, increasing the complexity of the task of the attacker and providing the response team reaction time to counteract the threat. Microservices and Service Mesh Linkerd (ISTIO). Microservices, also known as the microservice architecture, is an architectural style that structures an application as a collection of services. Microservices are independently deployable units, such as JAR, WAR files, OS executables, or Docker images. They have two forms of dependency: runtime, which affects availability, and design time, which impacts development speed. They allow large applications to be broken into smaller, independent parts, each handling a specific responsibility. Their adoption has increased with DevOps and continuous testing, as seen with companies like Amazon, Netflix, and Uber moving away from monolithic architectures. Difference between microservices and monolithic architectures. The monolithic architecture consists of applications built as large, autonomous units. Such applications cannot be changed easily because the entire system is heavily interconnected. Even a tiny modification to the code is likely to require creating and deploying a completely new version of the software. Monolithic applications are also difficult to scale, as scaling a specific function would require scaling the complete application. Microservices address these problems of monolithic architecture by taking a modular approach to software development. In simple terms, microservices reimagine applications as a combination of multiple individual, interconnected services. Each service runs a specialized process and is deployed independently. If needed, the services can store and process data using different techniques and can be written in other programming languages. What is a service mesh? It is a way of managing communication, accessibility, and data sharing between different parts of an application, especially in complex applications made up of many small services, known as microservices. Just as a microservice architecture enables multiple teams to work concurrently on different services and deploy them separately, using a service mesh enables those teams to focus on delivering business logic and not concern themselves with the implementation of networking functionality. In other words, service mesh is a dedicated infrastructure layer for managing communication between services in a microservice-based system. It handles inter-service communication through proxies, implementing features like encryption, load balancing, and observability. How service mesh works. A service mesh improves the manageability, observability, and security of microservices by using proxy-based communication. Proxies act as intermediaries, routing all traffic efficiently. Its architecture includes control plane, manages network policies, traffic routing, security settings, and monitoring. Data plane, handles data flow with sidecar proxies, which manage tasks like security and monitoring independently from the services. A service mesh architecture layer decouples communication from the application logic and uses a proxy or sidecar to manage communications between services and control plane. Web services typically interact through APIs left in the diagram, but a service mesh architecture, right in the diagram, separates those communications from the application logic and manages them through the control plane and a proxy or sidecar. A service mesh framework typically provides many use cases that make containerized and microservices communications more reliable, secure, and observable. Reliability, managing communications through sidecar proxies, and control plane improves efficiency and reliability of service requests, policies, and configurations. Specific capabilities include load balancing and fault injection. Observability, service mesh frameworks can provide insights into the behavior and health of services. The control plane can collect and aggregate telemetry data from component interactions to determine service health, such as traffic and latency, performance metrics, distributed tracing, and access logs. Security. A service mesh can automatically encrypt communications and distribute security policies, including authentication and authorization, from the network to the application and individual microservices. Centrally managing security policies through the control plane and sidecar proxies helps keep up with increasingly complex connections within and between distributed applications. Decoupled communication. A service mesh separates the network logic from the application or business logic of individual microservices, ensuring uniform execution and management throughout the entire system. Microservices and service mesh are important for ATLANTIS. Why? Because it will add an additional security layer to the ATLANTIS modules against incidents using redundancy capabilities. Within the context of Atlantis, it has proposed a microservice to be implemented in different containers, where each one possesses a different configurations, OS, architecture, and network topology. Therefore, in case of an attack, the compromised instance should be replaced using another configuration offering the same service with no perceptible changes from the perspective of the critical infrastructure user. This could be implemented and delivered with two different technologies, Linkerd and ISTIO. Difference between Linkerd and ISTIO. Architecture. Both products use a similar architecture. The key difference is the proxy used to perform this function. ISTIO uses the Envoy proxy, de facto industry standard with community, with 300+ companies making contributions. Linkerd 2.0 uses Linkerd 2 as its proxy, which has minimal industry support. Ingress. An ingress manages incoming traffic flowing into a Kubernetes cluster. ISTIO uses Envoy as the ingress. It provides solid functionality and was specifically designed for cloud-native and internet-scale API environments. Linkerd requires deploying a third-party controller such as Jinx to enable certain features such as rewriting incoming headers. Egress. An egress controls outbound traffic from a cluster. ISTIO controls outbound traffic using virtual service objects and gateways. Linkerd enables egress management, but it is not straightforward and can only be achieved through DNS and delegation tables, DTAB. Performance and scalability. ISTIO uses Envoy proxy, which is written in C++ and offers excellent performance. Linkerd uses a Rust-based micro proxy called Linkerd 2 proxy, which drives the entire data plane and offers good performance in smaller environments. Security. ISTIO provides generally superior security features, including HTTP and TCP support for mutual TLS, MTLS. In terms of policy management, ISTIO allows various providers to integrate their products into its policy management framework and supports setting rules to limit which applications can communicate with each other. Linkerd supports MTLS by default for all TCP connections. Monitoring. ISTIO provides monitoring through a tight integration with Kiali. Kiali is an observability tool that can generate metrics, infer network topology, and integrate with Grafana for advanced query capabilities. Linkerd provides out-of-the-box Grafana dashboards that provide insights into service communications. Community support. ISTIO has a strong community backed by major companies like Google, IBM, and Lyft. Linkerd has limited community support. It was created by Buoyant, which is currently the main corporate sponsor for Linkerd. You can find a more detailed description of these two tools in a dedicated video, also edited in the frame of the task T2.2 of the Atlantis project. Event-driven architecture, Kafka. The Atlantis project utilizes an event-driven architecture, EDA, to enable reliable, asynchronous interaction and data exchange between various systems and services, enhancing accessibility and integration. Events, triggered by changes in system states or inputs, are handled by producers and consumers. Producers detect events and send messages, while consumers, subscribe to relevant topics, process these messages. This architecture, exemplified by the EDA broker topology using Kafka, is loosely coupled, facilitating real-time or near real-time responses to significant occurrences without the need for synchronous communication. EDA components include producers, topics, brokers, and consumers, with message queues ensuring reliable message storage and processing. The Atlantis system uses Apache Kafka for high performance, low latency, and fault tolerance. Kafka's distributed log architecture ensures scalable, persistent message storage across multiple servers, enhancing availability. Events are stored in topics, supporting multiple producers and consumers, with partitioning for scalability. Kafka offers advantages such as improved I/O performance, horizontal scalability, data redundancy, high concurrency, low latency, high throughput, fault tolerance, batch handling, and default persistence. This is an overview of the EDA pattern schema plan to be implemented in Atlantis framework. The advantages are many. Decoupling promotes loose coupling between system components, enhancing resilience by isolating failures and preventing cascading issues. Resilience enables services to operate independently, unaffected by the status or health of other services. This ensures continued application functionality, even if individual microservices fail. Flexibility. EDA's adaptability allows seamless integration of new features, data sources, or modifications to existing components without significant disruptions. Scalability. dynamically adjusts to handle growing event volumes or changes in system load without sacrificing performance. In Atlantis, dot notation is used for topic names to improve readability and clarify relationships between topics. Each component has specific topics structured by layer, component name, and information type. To ensure interoperability, Atlantis adheres to these guidelines. Consistent JSON format. Messages follow a standardized JSON structure with common attributes and component-specific data. Unified alert format. Alerts use the Unified Alert Format UAF based on the IDMEF standard RFC 4765. Autonomous publishing. Components publish data immediately to the broker for asynchronous distribution to consumers, preventing blocking. Topic-based classification. Messages of the same structure are categorized by unique types within topics for easier validation. Validation. Consumers validate messages using JSON schema validators to maintain system integrity. Version control. Message specifications evolve with documented version numbers and headers to synchronize across stakeholders. That's it for the presentation of the work related to resiliency and self-healing by design performed in the frame of the Task 2.2 of the Atlantis project. Thanks you for your attention. CS Group would like to thank the other partners of the task who contributed to this video: ATC, Engineering, JSI, Siemens, and Vicom Tech.